Okay, welcome everybody to this February Journal Club, well, seminar series. It's a huge pleasure to welcome friends from the other Cambridge online to this. So Raffaele Ferrari and Paul O'Gorman from MIT. I think they're going to be giving us a double act today. So, but I think Raf, are you starting off?
How do you want to do it, Paul?
Oh.
You're muted. So.
I was going to start and...
Oh, you're going to start. I'm sorry. My apologies, Paul. I got it backwards. Yeah. Okay, Paul. Why don't you start?
Sure.
That'd be great.
Let me share my screen. Okay. Move this over a bit. So yeah, so I'm going to talk about what's called a Climate Grand Challenge project at MIT. There's several of these. I'm co-leading one and Raf is co-leading another, and we have some overlap also. And yeah, so I will discuss this one and then we'll change over to Raf. So this one is about climate and weather extremes. The title is Preparing for a New World of Climate and Weather Extremes. I'm one of the co-leads, also Professor Miho Masaru, who leads the MIT Urban Risk Lab. She's an architect, works on disaster recovery and other related topics, and Kerry Emanuel, who's another professor from my department. And so we're focusing on the tails of the distribution of the extreme events, which we know already have major societal and economic impacts, and many of them are expected to intensify with climate change. So there's a few different ways you could show this. One, in terms of economic damages, is to look at the number of billion-dollar disasters, which are kind of monitored regularly. And so on the left, this is the total number of them per year. This is adjusted for inflation, just mentioned, and these are water-related disasters, roughly speaking. And you can see, there's an increasing trend in the number. If you look, up to today, the year with the greatest number is 2023, so it has kept going up. And you can see especially in the total damages, you can see years, hurricane seasons that are particularly notable, like 2005, 2017. But in terms of actual the number of such events, it's actually severe convective events, so hail, tornadoes, etc., wind damage, that's actually dominates the total number. But then the total cost tends to go with the really big hurricane years. I'm showing the amount of money, not because that's the only metric that matters. Of course, you could look at deaths or other estimates, but this gives a general sense of what kind of disruption these events are happening and how it's changing over time. It's not just, of course, climate change that matters. Changes as you have growth, economic growth, you also have an impact where people live, infrastructure, etc. But climate change is certainly part of the story here, and it tends to have very large uncertainty when you look at projections for the future. And so the other reason we want to, the challenge aspect of this, that it's the rarest events that really have outsized impacts. So two events that, I think really stand out were Hurricane Harvey, which, broke many rainfall events from a stagnating hurricane. And then the Western North American heat wave in 2021, which again broke a lot of records, many deaths, etc. So these are kind of events, or some of the kind of events we're interested in. They're difficult to estimate the risk, they're challenging to model accurately, and they're challenging to adapt to. And so that's what we want to focus in on in this project. And so our project then, I'm showing is kind of outlined here. There's three parts. One is climate science and risk modeling. That's the part that Schmidt Sciences is helping to fund. But it's tightly linked with two other parts. One part is adaptation for cities largely. That's led by Miho, who I mentioned earlier. And a third part, which relates to infrastructure and energy systems. So why this comes in is we're also interested in mitigation of climate change. And one of the ways we can mitigate, of course, is transitioning our energy system to more renewables or clean energy in general, but also renewables like wind and solar, which are vulnerable to extreme weather and climate, just as our whole energy system is. But as we transition the grid, this is a big factor. So I'll talk about these parts one by one. So the first challenge is we don't adequately understanding the changing risk of extremes at the regional scale in particular, and for the most impactful events. So I work a lot on changes in extreme rainfall. And, you know, if you look at, say, the IPCC report, a lot of the information we have is at continental or global scale. But if you look regionally, for example, for the US, there's certainly a spatial pattern to the changes, with the biggest increases happening in the Northeast, where I'm located here, and much less so in the West. People have tried to understand this pattern, but I would say it's fair to say we still don't understand it. Is this going to be a persistent climate change pattern? Is this just internal variability we shouldn't worry about? And so this is one of the kind of things we'd like to understand. So our first two objectives following from this are to reduce key scientific uncertainties related to extremes. This would just be one of them. And then the second one is to develop improved tools for assessing risk of extreme events in specific locations that can be used by stakeholders like city governments or communities in general. The second challenge we're addressing is what about adaptation? So there is, of course, progress in adapting to changing extreme weather and climate, but I would say it's fair to say it's fairly slow relative to what we need to do. And more importantly, it's generally for the best resourced communities. And so part of dealing with this is making sure the climate science and tools you develop can scale, that they're not so expensive they can only be used for one well-to-do location. So we're focusing on a few different places: Boston, which we know well, Broward County, Puerto Rico, and Cape Town, and trying to work there. Mio and her team are working with communities directly in terms of workshops. They're working with government and agencies and trying to help them adapt using information that comes out of this project as well. And then lastly, I mentioned about the energy system. We know that's rapidly changing. It's vulnerable to extreme weather events. And here we're focusing on wind and solar. And the aim is to address vulnerabilities so as we can plan the energy transition better. And so one I thought was very interesting came out of Jessica Transek's group, who's part of this project, with her postdoc, Micah Ziegler. That's the time series you can see at the bottom. So what this shows is the state of charge of a storage system. This is a modeling of that for a mix of wind and solar energy over time. And notice it's a long time, it's over 20 years. And this is for a location in Iowa, but you know, this is fairly generic behavior from their studies. And why the storage state of charge matters is that you want to, you know, size your storage, your battery capacity, such that it will deal with the kind of events that will happen. And so those are indicated here by these black triangles when the storage reaches to a very low number. You know, there's more to it, there's transmission, et cetera, but this is still a very interesting number. And you can see it's only a handful of events that are determining how you might want to size your storage. So what are those types of events? They've been looking into it. It's not high wind events like we've been talking about so far with, say, tropical cyclones. It's actually low wind events that might last, you know, for 30 days or so. And so there's particular type of events that matter, and it varies, you know, depending on what part of the country you're in or what continent you're on. There are very different types of events that matter for this. Okay, so let me talk a little bit more about this component that Schmidt Science is involved in. So, you know, as I said, it's reducing these key scientific uncertainties related to extremes and developing tools for assessing risk of extreme events in specific locations. So for reducing key scientific understanding, we're looking at changing heavy precipitation events. I showed a graph of that earlier. Talia Tamron-Brodsky has been looking at temperature extremes. So there's been a lot of interesting work lately on trying to see, is there some sense of an upper maximum on heat waves from the dynamics, and she's been looking at that. And then Kerry Manuel and his group have been looking at convective storms, which, as I mentioned, is the greatest number of billion-dollar events, for example, is coming from those type of storms. And so that's the bulk of it, but we do also are looking at past climate. The reason to include that is we want to improve understanding the risk of extreme climate change, if you want to put it that way. And that's hard to assess with models alone for sure, but you can look to the past climate. Here on this time series is showing hyperthermal events, roughly in the Eocene period, where there's large abrupt changes in the carbon cycle. And so we know these have happened. Some of them have been associated with kind of marine extinction events. But there's no perfect analog for what we're doing now in the modern time. It's different length of time over which it's happening. It's a different magnitude. And so Dan Rothman, who's leading this work, has some really nice papers showing how you can kind of rescale events and put them onto a similar scale, even if their time scale, for example, is different. And so using that to try and understand what is the risk of what we're doing now in the modern time. In terms of then developing tools to assess the risk of current and changing extremes, I mentioned 4 things here. On the top left, this is an extension of work that's been done by Kerry Manuel's lab for a number of years, what he calls statistical dynamical modeling of tropical cyclones. So these are tropical cyclone tracks. And the idea is to generate a lot of tracks and intensities, so as you can, in a Monte Carlo sense, so as you can evaluate the risk. So he's pioneered that. It's a fairly common approach and is still working on using that and improving it. And then we want to extend that kind of idea to extratropical cyclones. You definitely can't just do the same thing with the tracks. They're too large and too much interacting with the flow. But the basic idea is to generate large catalogs of extratropical cyclones efficiently, so as you can estimate risk. There's also work, so that's with Kerry and Sai Ravella, who's a research scientist at MIT. Sai's group is also looking at machine learning, which I'll talk a little bit about in a couple of slides. So improved methods to downscale from relatively coarse to very fine scales that you may need. There's also part of our work, which we're still spinning up, that's climate model emulators. So I won't talk about that because Raf is going to talk about that in his project. But the idea here would be to include the tails of the distribution as best you can. And then lastly, rare event sampling algorithms. So these are approaches to more efficiently sample the tails of the distribution, and they can be wrapped around, for example, a general circulation model. So here's an example where it works well. You have a return level on the y-axis and a return period. And the normal way to sample, this is in a toy model, just to illustrate, the standard way to estimate the return level would be, or return period would be, to run a simulation, say with a physical model, a very long time. And that's what's shown in the gray envelope here. But an alternative is to use rare event sampling algorithm, where you run an ensemble of simulations, but when you have some metric of how they're approaching a rare event you're interested in, you clone some of them, you kill off some of them, and you keep track of the probabilities. And so that gives this red estimate here, which goes out to much longer return periods and has narrower uncertainties for the same return period. So this is great if you can do it. And the challenge is, can we do that for weather events we're interested in? So yeah, so this project is ongoing. It's exciting. So far, a lot of the work is going well, but I don't have results to show yet. But we do have a few research highlights I wanted to share with you. So one of them was the downscaling I mentioned that Sai's group is looking at. So there they want to downscale extreme rainfall events here from era 5, which is here coarse resolution to intermediate resolution to very high resolution. And this is in one location. The challenge here, if you want to do it for extreme events and do machine learning, is you don't have much data in your observational record. And so you have to be much more clever about it. One way that this paper is clever about it, as it were, is by including the physics of orographic rainfall as one of the inputs. So it's a generative approach, but it's using that as one of the inputs. And there's other aspects of what they do so that you can still do a good job when you don't have much training data. For the rare event sampling, I already mentioned that this is work led by postdoc Justin Finkel. As I mentioned, you're running an ensemble of simulations. You're cloning some that are going towards extreme events. You're killing some that are not interesting. But one of the main things you have to do is you say, take an ancestor, you have to perturb it when it reaches a certain level. This could be temperature, for example, or rainfall. And then you want to get a descendant that explores the space where extreme events are happening. But one problem you see if you try to apply, which we did, a standard algorithm called adaptive multi-level splitting to a general circulation model, is that because of the Lyapunov time for that model, so how quickly trajectories split apart, by the time you do get a good splitting apart of the trajectories, you haven't really changed the extreme event you're interested in. So this is a problem of timescales. Freddie Boucher has worked on this for longer term extreme events, like a seasonal temperature anomaly, and you don't have this problem because your Lyapunov time or separation time is much shorter than the 90 days he's looked at. But if we want to look at, say, daily events, this is a big problem. So what Justin's been doing is splitting early, not when you reach this threshold as the standard algorithm would say you should, but rather much earlier. That has the big advantage that you can get a descendant that is boosting your extreme event a lot. It has a disadvantage that you may not reach the level that you need to reach. So you have to have a rejection step. And this falls in the framework of what's called subset modeling, which is done in reliability engineering. And so we can still do it. It costs a little bit more because you have these rejections, but it does seem to work in the tests we've done so far. So we're exploring that, and you can read about this in a paper on our website. And then last example involves convective storms, which, as I mentioned, is interestingly in the last few years has really been a big source of damage and deaths in the US, for example. Kerry's been working on this. It's kind of a preliminary step in a larger project to understand causes of severe convection. And Kerry's idea, which is pretty interesting, is to look at the role of soil moisture. Here he's highlighting, which is shown here. Here he's highlighting places where wet soils are downstream of dry regions. Say here, for example, and here it's pretty obvious. And those are regions where you get a lot of severe convection. And so he's been trying to work on one of the ingredients for severe convection, which is high convective available energy. To what extent is soil moisture playing a role? Soil moisture is very interesting because it would perhaps have some predictive power. Severe convection is kind of generally considered a very difficult thing to model in terms of risk. So you can read about that in this paper here. Yeah, so that's the highlights I wanted to mention. This work, I've highlighted the part that Schmidt Science is involved in, but it's also feeding into and informed by the work in the other areas. We have a website if you'd like to read more, climateextremes.mit.edu. Also, I'm happy to talk with anyone about this work. I can be contacted at pog@mit.edu. And I'll also plan to be at the cross-VESRI meeting this summer in the other Cambridge, as it was called earlier. And so I'd be happy to talk to people then. And so that's all I had. I'm going to stop sharing so Raf can take over, and also so as I can see people a bit better. But yeah, thank you.
Great, thank you very much. So if there's no more questions for Paul, let's hand over to Raf.
Okay, can you see the screen?
I can, yes, and the
Okay,
music's
wonderful.
working and great.
Okay, so I am going to present work that is done, is largely funded by Schmidt Sciences. And as I put in the title, it's two parts. It's making climate projection both more accurate, but also more accessible. The more accurate part is part of the Climate Modeling Alliance project, or Clima as we call it, which is a collaboration between Caltech, JPL, and MIT. And the colleague is Tapio Schneider, who I think is online. The idea there is to improve the accuracy of climate models by building a new climate model. And I get a bit in detail of what that means. The second part, the project is really focusing on this climate grand challenge at MIT. We call it the Bringing Computation to the Climate Challenge, BC3. And here the goal is instead to make projection accessible to decision makers that might want to explore different scenarios or the impact of different intervention, but to get results in fast time scale. And this is work that is, I call it with Noel Selin here at MIT. Oops. Can't I go for? Okay. So starting from the Clima project, and here I'm really going to summarize some key results. And in particular, I'm focusing on the work done at MIT, but there is much more that is happening at Caltech and JPL. But the overall strategy of the whole group is that the goal is really to reduce the uncertainty in projections associated with the parametrization or the representation of subgrid scale physics. And because we know that at least until mid-century and probably beyond, that is the leading contributor to uncertainty in our projections. When you want to reduce that uncertainty, you can go one of two ways. Both are advocated strongly in the climate community in general, and in the Clima project, we are adopting both of them. One is, well, if you can build faster models that allow you to use a smaller mesh grid, then all of a sudden you need to parameterize less of the subgrid scale physics just because you resolve more of the physics of the climate system. And we've gone in that direction by leveraging the Julia language that allow us to easily take advantage of GPU architectures that we know now are more performant than traditional CPU architecture. I'll show an example in the next page. The other way you can improve the representation of subgrid scale physics, because no matter where we go, there is always going to be physics like clouds, like boundary layer turbulence in the ocean, that will not be explicitly resolved on the mesh grid of a climate model. So some parameterization will remain. But what we can do, and this is what largely led by Caltech, in particular by Andrew Stewart's group, is to develop efficient calibration methods that allow us to use the wealth of observations we have of the climate system. And by that, I mean satellite observations, balloon data from the atmosphere, float profiles in the ocean, hydrography in the ocean, and leverage all that amount of information to calibrate the parameters that appear in subgrid scale parameterizations. That's a computationally very heavy work. So the technological or the mathematical innovation in the calibration process is really where one can make a difference. But if you can do that, then we have physics, subgrid phase physics that is really calibrated with the available observation, something that we don't quite do today. We generally use subset of observations because we can't cope with the whole amount of data. So to show where we are, and again, as I said, I'm focusing on the MIT side, but there is a lot that could be said about the atmospheric and land models. Here I'm focusing on the ocean models, which is what we do at MIT. Largely thanks to two people, Simone Silvestri and Greg Wagner at this point, but with other people contributing earlier on, we developed a new code called Oceananigans, and it's an ocean dynamical code that runs efficiently on GPUs. So just to give you some ideas, we're talking about simulated years per day. We run at a quarter of a degree. The model can simulate 10 simulated years per day on 4 GPUs. If you compare that what the state of the art today, you could run 10 simulated years per day on, should be able to see it, 2,000 CPUs. In terms of comparison, that means that in terms of energy cost, that's a factor of 40 less. I'm talking about 10 simulated years per day because if you think that you want to run simulation for about a century, that means that you already have to wait 10 days for one simulation. you probably want to run hundreds of simulations to look at internal variability in the system, or in our case, to do calibration. So that puts a bit of a limit that if your model is much slower than that, you can't really do what we would call climate simulation in the whole sense of running ensembles and doing calibration. The advantage of oceananigans is then we can also move and run now at 12th of a degree. That requires, achieves 10 simulators a year per day now on 64 GPUs. If you think that machines like Frontier have tens of thousands of GPUs, you can still achieve that. So now we moved from state-of-the-art at a quarter of a degree all the way to 1/12 of a degree. We can still do that, both the calibration and the ensemble simulation we need. And you're seeing one of these global solutions on the left-hand side. And that is a solution run at a 12th of a degree. We can, of course, run at even higher resolution. Of course, the performance at some point goes down. So I'm saying that 1/12 of a degree is the highest resolution that we could run for climate-like simulations. And so what happens when you do that? And we are looking at the top part of this slide. In terms of the physics that occurs in an ocean model that is relevant to climate simulations, we have large-scale currents at scale of larger than 100 kilometers. That's where only an ocean component of a climate model would resolve these days. Then we have mesoscale turbulence. These are the geostrophic eddies in the ocean on scale between 10 and 100 kilometers. These are the equivalent of the cyclone and anticyclones in the atmosphere. State-of-the-art ocean models today have a resolution of 25 degrees, so they resolve part of that spectrum, but then they still have to represent the part that they are not capturing, so we are not quite there yet. When we're talking about physics at even smaller scale, we have upper ocean fronts between 1 and 10 kilometers. These are the equivalent of weather events like the storm that is passing in the northeastern US right now, a set of fronts. They also exist in the ocean at small scales, and then boundary layer turbulence on scale less than a kilometer. So in state-of-the-art ocean models, as I said, essentially you're only resolving the large scales. Everything else needs to be parameterized in some form. By developing this model that runs on GPU oceananigans, now all of a sudden we move the bar here where we are resolving the geostrophic turbulence largely. And so what we need to parameterize is upper ocean fronts and boundary layer turbulence dynamics of smaller scale physics. That is a big achievement in a sense, because one of the problems with geostrophic turbulence is that it's very non-local. Like cyclone and anticyclones, geostrophic eddies meander large distances in the ocean. So in a sense, the closure problem has defied our attempts for the last 40 years. In some sense, progress has been made, but it's still hard because you need very large ostensives, or it's not clear exactly how local closure could operate. While the processes that still need to be parameterized in a model like oceananigans are much more local in space. And so there is hope that closure can be better calibrated and they are not as challenging. And to give you an example of how we are moving in oceananigans now to represent and improve the representation of this subgrid scale physics, for example, I'm giving you an example of how we represent boundary layer turbulence. And the first step was what we want to represent is the turbulence and the rate at which properties are being mixed by the turbulence that is generated by surface air sea fluxes like heating, cooling, and momentum stresses by the winds. A new model was developed for this parameterization boundary layer turbulence called convective adjustment and turbulent kinetic energy, for short CATKI. That is representing essentially a diffusion equation in the vertical for temperature, where the diffusivity kappa, the rate at which you mix, depends on the forcing, and it's formulated in terms of a mixing length and a prognostic equation for eddy kinetic energy. But that equation will depend on a number of free parameters, things about Richardson number or Prandtl number and various forms that we don't know a priori the value of. And so how do we choose those parameters? Well, we run a library of very high resolution simulations for the moment. And so here you see two examples, one first with a strong wind and one with strong cooling. It's a box of a kilometer by 500 meters by 500 meters. It's very small, but we resolve the full turbulent physics. These are run with oceananigans, which I didn't mention, but it's a model that can run hydrostatic simulation on large scales, but also fully non-hydrostatic simulation on small scales, efficiently, again, on GPUs. So we run simulation where just let the full turbulence develop, and then we can take a zonal average or an area average of this profile, because essentially this block would fit in a fraction of a grid box of a climate models. So the climate model can only represent the vertical profile of temperature of that whole area. And so what we do is that then we have a large ensemble of libraries for the kind of surface we might expect to see in the ocean. And then this would be depth. This is, let's say, a temperature profile. And by taking an area average of this solution, we get a vertical profile. And now we tune the parameters of our parameterization such that it can reproduce the temporal evolution of that profile just in the vertical. So you went from a full three-dimensional expensive solution to a parameterization that is one-dimensional and just predicts the vertical profile of temperature. And we can calibrate using a sample carbon filter approach that I mentioned are being developed largely at Caltech to reduce the difference between this library of simulation and the prediction for our one-dimensional parameterization. And then once you've done this exercise, you test on a number of new turbulent simulation of this kind to see that actually we have extrapolation capability, which is the main point of using parameterizations. And we've shown that you can actually get very good performance. Now we are putting this parameterization in a global ocean model. This is being done as we speak, where new biases might appear because now there is interaction between the parameterized physics and the large-scale physics. And so we're going to do a second calibration that uses the values of the parameters we have now as priors, and we're going to try to improve in a fully ocean-only simulation. And then we'll have to repeat the exercise when we couple to the atmosphere, which is in the year to come. Ocean iron guns is, as the part that I described, is just the ocean physics, but we are also working, especially through funding through Schmidt Sciences, through VESRI, on implementing a biogeochemistry model. We already have a biogeochemical model that is being developed in collaboration with colleagues at Cambridge, England. This model is mostly for regional study in the sense the use is quite expensive in the use of tracers. We are also developing a second version of the biogeochemistry model, which is going to be a simplified version of the previous one, because when you want to run global simulations on GPUs, memory footprint is a problem. So we have to be cognizant of just reducing the number of tracers that we strictly need and not overdo it. We're also developing a sea ice model. Greg Wagner has been leading this, and you can see some simulation around the Southern Ocean with sea ice coverage. And then a lot of the work is now in developing this module, Clima Ocean, which is a coupled ocean sea ice module. So we can run essentially what we called OMIP simulation of the full ocean system, the dynamics of the ocean systems that then we can couple to an atmosphere. Okay, so this was the work done in trying to build the new climate models that, since it's going to be calibrated against high resolution simulations and observation, we suppose we have more skill in future projection, and we're going to start probably calibrating against properties like the seasonal cycle. Probably we know that models have large biases, and start reducing and progressing, moving to longer time scales. But now, even once we have a model that we believe is more accurate in its projection, and we'll be able to quantify that, there is still a problem that if I'm a decision maker, and let's look at this left bottom figure, these are supposedly as a function of time trajectory, emission trajectories that were chosen by the Intergovernmental Panel on Climate Change as an intermediate emission scenario. Let's say this is pathway A, this is, let's say, cumulative, emissions of greenhouse gases, equivalent CO2. There is a high emission scenario pathway C and a low emission scenario pathway B. For each one of those, the IPCC is producing an ensemble mean projection that you can look at what you might expect the climate at the end of the century, for example, would be for that particular emission scenario. But if you're a decision maker or maybe an entrepreneur, you have an idea of how you might be able to reduce emission along this orange line. Now, the problem is that there isn't a simulation that was really following that orange line, but you still would like to assess what the impact of your particular choice would be. And so the idea of emulators is that you want to create numerical models that are going to be very cheap to run. So we want output in a matter of seconds that are trained on output from large-scale models, and they essentially are able to interpolate in between emission scenarios. So that this is between pathway and pathway C, and if I know what happens in these two pathways and I have a way to generalize, I can predict what the outcome, for example, the regional pattern of temperature will be for this intermediate scenario. And that's what we are working on in the part of this BC3 project that is funded by Schmidt Sciences. So just to give you an idea what a simple emulator could be, the approach that has been used effectively is what is called pattern scaling. And the idea would be that if I want to know the temperature change at every point on the planet, I can assume that it scales linearly with a change in mean global temperature. And so this is just a linear relationship where the coefficient A and B, meaning the slope and the intercept, are just a function of space. You might think that this is a bit too simplistic, but you can do exercise like this. And again, I write names underneath. Paolo Gianni is the person who's been leading this work, but in parentheses, I also put all the other people that are involved in that project, and you'll see it slide by slide. So for example, for a mean temperature increase of 3 degrees C, this is the projection of the regional pattern of temperature change since pre-industrial time from the 1850 here, predicted by the emulator that was trained in particular with the NCAR's ESM model here. And now we can look, well, is that emulator, does it have skill in predicting temperature changes for after a full century of warming compared to the original model that it was calibrated against? Here it should have said CSM. So now we're changing the temperature change predicted at every point minus the temperature change predicted by the full numerical simulation. This is a scenario that the model was not trained on. And what you see is that pretty much everywhere the error is about half a degree or even less, except higher latitudes where there are aspects the response is not as linear. It has to do with, we believe, sea ice in particular changes in the area that makes the response not quite as linear, but the emulator is quite effective. Now, this is still depending on changes in mean temperature. You say, well, I don't know that change in mean temperature, and an approach has been taken, and this is work led by Björn Lutyens and other postdoc in the group, is now we're training against, we're looking at output from the Norwegian ESM. There is a reason why we use that. It's what is used for climate bench, and we'll see in the next slide why I want to compare with that. But this point here is true for any ensemble of models you might look at. Here I'm plotting now the cumulative emissions, so the integral of emissions as a function of time from 1850 to the end of the century for 5 emission scenario considered by the IPCC. And in the middle panel is what the Norwegian ESM is predicting as the temperature change associated with that emission scenario. Same colors mean same emission scenarios. Now, the main point that is being made is here, is that if you look at the mean global temperature change as a function of cumulative emission, the relationship is nearly linear. So what you can do is that you can replace in your emulator the mean temperature change with the cumulative emission. So now you're really relating temperature patterns around the globe to just cumulative emissions. And you think you should be able to do a reasonably good job because of that linear relationship that tells you that indeed there is a linear relationship between the change in mean temperature and the cumulative emissions. And here we show what happens if you do that exercise. Now this is the true surface air temperature from the Norwegian ESM model, the difference between the temperature at the end of the century minus 1850. And this is the prediction of the emulator on this emission scenario. It's an intermediate emission scenario, while the emulator was only trained on the high emission scenario and the lowest emission scenarios. And again, if you take the difference, you see that the model does reasonably well in most latitude, but high latitudes, again, the discrepancy can be as large as 1 degree. Now, that has prompted the machine learning community to try to improve on this simple linear emulator and do the same exercise against cumulative emission, but trying to use something that doesn't essentially make a linear approximation. And the climate bench one is this archive data. Just make it easy to use this Norwegian ESM model to do this calibration because the data are already prepared for you. And they tested a number of different approaches over time, started with Gaussian processes, neural networks, convolutional neural networks, random forest, all the way to Clima X, which is now a foundation model that uses vision transformer architecture. So we're really getting a cutting edge artificial machine learning techniques. And as you move on, the number of free parameters is increasing up to hundreds of millions. And here what we point out is that if we use this simple linear emulator up here for the same exercise, we essentially do better than pretty much any of the more sophisticated machine learning algorithm, at least in regional patterns predictions, less so on global pattern when you look at the variance on the global pattern. So if you look here, I'm not expecting you to look at this number, but here are just standard errors in the full temperature pattern predicted by the model minus the one simulated by the Norwegian ESM. And you see that typically the error is smallest for the linear pattern scaling. This is just brought up to suggest to us that one should use a bit more principled approaches to figuring out what parts of the physics are really missing in emulators and try to build that into improving the emulator instead of just throwing necessarily very high computational cost approaches that are not guaranteed to deliver as much in terms of improved performance. So the first thing we looked at, this is work led by Lisa Fries, a former student now at Berkeley, but that worked for us the first year. And here the idea is that, well, one thing that we know that is ignoring this cumulative emission approach is that there is memory in the system. Greenhouse gases don't enter and leave the climate system. So you might want to rewrite the formulation of your temperature change as the convolution of what we call, in mathematics, you would call a green function at each point that convolves the emission scenario. In particular here, the problem was done quite easily. There are a number of simulations now they were using against the CESM model, where they've done a number of simulations where they have impulse CO2 experiments. You just all of a sudden put a spike of CO2, so that's essentially giving you a green function response. You have a Dirac delta forcing and you look at the response, so you can just estimate the green function. Once we have a green function every grid point, we can do this convolution, and I could show a number of examples. I just chosen this one just to convince you. So let me explain what this is. This is the temperature increase, for example, in Boston, or you could look at Buenos Aires, Lagos, or Shanghai. The red line is the temperature increase predicted by our emulator, and I'm not showing it to you, but I hope you can believe me that it actually has pretty good skill against direct numerical simulation run with CSM. And again, I'm showing a prediction against a number of scenarios that weren't used for the calibration. And the red line is for a scenario where the model is increasing the emission by 1% per year, CO2 emissions. The other lines are instead situations where you are emitting at different rates, but you see a dashed line at year 70 or so. At this time, all the emission scenario achieve the same cumulative emission of CO2. So according to the pattern scaling emulator, at this time, it would predict that all models achieve the same temperature at that location because there is no memory in the system. Instead, here we see that if we use different models, different emission scenarios, different emission trajectories, you end up at pretty different temperatures, at least in the Boston area, at 70 years. And the difference can be up to, well, close to a degree, a complete degree, which is nearly as large as the trend from beginning of pre-industrial time. So it tells you that indeed the history does matter, that there is a memory effect that you have to include because the system might respond. So in terms of decision makers, it's not just knowing the total cumulative emission, but also the trajectory you follow to get to a total cumulative emission that matters, and that might have serious implications for different regions. And you see that they are different in different parts of the world. Moving on, these models so far have focused on individual trajectory. We know that there is a lot of variability in the climate system, so we want to have probably emulators that don't just give an individual trajectory, but a full distribution. So we are moving on in emulators that predict distribution. So here, for example, I'm showing two examples very quickly that use what we call principal component analysis, or if you want EOF analysis, where you take your full data set, so your whole set of simulations for a particular scenario. Here we are using the MPI model, the Max Planck Institute model, that has many realizations, 100 realizations per emission scenarios that we need for this work. When you do the principal component analysis, essentially you're dividing your data in a set of modes. So these are two of the modes, for example, that we got for a particular realization, and they have a special pattern. And then they also have a temporal amplitude that modulate this pattern, right, that I'm showing in the second line here. So what we're going to do, well, first of all, why did we project on principal components? Well, here we want to give you a full distribution. So at some point we want to compact the amount of data if we want the emulator to be efficient. So by using just the principal component analysis, we just are going to take the first 30, 50 modes, not all of them, that give the main patterns of variability. Now we have the amplitude of the modes. We are going to represent the amplitude of modes in terms of a mean and a variance, which are assumed to depend only on global mean temperature, equivalently on global emissions here. We are not putting memory, but we will. And so our AI now is represented as a mean that depends on global mean temperature, a variance that depends on global mean temperature, and then multiplied by this term. This Lij are the correlations between the PCA modes, and Wi is a noise. And so this is where the stochastic component comes in. We have a noise that can be white noise, or we use color noise, where the spectrum is chosen based on the spectrum of the MPI model simulations. And so now we can reconstruct, for example, if we've done the PCA analysis, this is work led by Mengse Wang, postdoc, where he looked at daily max temperatures. So we can now just predict daily max temperature distribution as a function of time as the climate gets warmer. Or we've done it for local monthly variables. So now we are pushing more like not just temperature, but precipitation, moisture, and other variables, again, using the same approach. And we can give you the statistics. And this is work really led by a student, Gosha, and Andres Souza, a researcher in our group. And so what do you get out of these exercises? But you get something like this. For example, this is the PDF of maximum daily temperature in Boston in the decade between 2050 and 2060. You see, we don't get just one number, 26 degrees or so, but we get a whole distribution. You can get any other is as warm as 35 degrees in the June-August period. The blue line is the prediction of the emulator, and the dashed red line is instead the result from the MPI ensemble. Same for different regions. But I really want to conclude now showing you a bit where we are trying to go and where we are at. In a sense, we really want to make this exercise useful for decision makers. So we need to connect this regional prediction of this emulator to questions that decision maker may want to make and test. I guess maybe a good example, at least in the US, people have followed this summer. It was Senator John Kennedy that caught the Deputy Secretary for the Department of Energy asking, well, if we spent $50 trillion to eliminate emission or get to a zero carbon emission economy in the United States, how much would the temperature of the planet change? And understandably, there wasn't an obvious answer. We want to provide tools that might get you to the point where you can give these answers. And so here I'm going to show a bit the results from the emulator for monthly temperature change that I described before using a Gaussian regression, a Gaussian process. But now we're coupling it to En-ROADS, energy roads. This is a model developed by the group of John Sturman here at MIT. And Bethany Patton is the person that is mostly connected with us. So what this model does is produces emission scenarios. So this is emission of different greenhouse gases. And well, actually, this is the portfolio of energy resources that you get from which they compute the emission scenario. But now you have a set of dots where you can make choices as a decision maker about what intervention you can use. And of course, we can, this is a subset of everything you can do. But let's say that this is business as usual for an emission scenario, and that gets you at the end of the century to a 3.3 degrees global mean temperature change. And let's say that you're a very skilled politician that has figured out how to convince Congress to impose a very high carbon price and pass it, which is probably unreasonable, but let's say that that's what you can do. And then the tool right now, all it tells you is that, well, if you have a very high carbon tax, you can reduce temperature to 2.54 degrees, but that's a global mean temperature, which might not give you the level of detailed information that you need if you want to convince people or make a case for what local interventions are. And this, for the moment, I'm showing you temperature, but we could show precipitation or other variables that we're working on, and then becomes even more directly relevant. So for the moment, this is a bit clunky, but we are developing a good API as we speak. So let's say that I want to know what is the temperature change that I would expect compared to pre-industrial time from 1850 for the month of January. I said I could do it for every month. And now I can go and look, and this map on the globe, this is the United States. I can look at what the temperature change. In particular, I could ask if I want to know what is the change of temperature in the United States. Well, maybe since we have people from the United Kingdom, we could go to United Kingdom and say Cambridge. Oops. And I have a map here that I can zoom in. And it tells me, for example, in Cambridge at the end of the century, due to this emission scenario, the temperature change will be around 2 degrees. Now, I don't have to stop here, because probably what I care the most about, if I was somebody advocating for this intervention in the UK, now I can ask, well, the more relevant question might be, how much did I decrease the temperature compared to business as usual by increasing this carbon tax? And here it tells me, well, the temperature decreases by 0.7 degrees. So that's impact locally. This is for the ensemble mean of 100 realizations. Now you can ask, well, and this is the advantage of having a stochastic model. Every year might be different from another year. And from the model ensemble, we have an estimate of what that uncertainty is. That was the noise we included, the variance, right? So I can run, for example, one particular realization. In this case, for this particular year, it shows that the temperature might have decreased by close to 2 degrees. But then I can generate another sample year, and the temperature in that winter instead hardly changed at all compared to the non-intervention scenario. So it also gives me a bit of a sense that people should expect the year to year. We know that every winter is different from every other winter, or if I want to explore, every summer is different from every other summer. And that tells me what is the impact of my intervention in summer months. And again, as I said, now we're looking precipitation, another variable that might be more directly relevant for decision makers. How do I go back? And I may just leave some conclusion of where we are at, and I'm happy to take questions, and for me or also for Paul, I guess. Not much time left, though, sorry.
Well, wonderful, Raf. Thank you. That's an amazing tour you have there. They're quite. It's not chilling. It's getting hot. So, does anybody have any questions? I'd really like to thank the two speakers for an absolutely wonderful combination of talks about the MIT Climate Grand Challenge. It is very, very impressive, the stuff that you're doing, and really is addressing the real challenge of not only that the climate is changing, but understanding how it's changing and how we're going to survive the next few decades. So thanks so much to both of you, and thanks to everyone. It was really brilliant talks, and have a good, well, it's all going on, isn't it? It's Mardi Gras, tomorrow's Valentine's Day, you know, enjoy your pancakes and your entertainments over the coming days, and see you all next month. Okay, bye-bye.
Thank you, bye-bye.